Today we are going to talk on a topic of blast furnace slag. It's basically fundamental. We will discuss control and practical impact. So as you must be knowing, for a start, we can rephrase this line that if you take care of the slag, furnace will take care of the rest. So by end of this session, you will understand what slag really is, why it matters, and how we control it, and what happens to it after it leaves the furnace. So let's get started. So as you can see, that slag is just not waste. It's a complex, high temperature mixture of oxide. On this slide, you see the main players, acid like silica and alumina, and bases like lime and magnesia. Both are segregated in different columns, and even some iron and manganese oxide. So, what's the interesting is that oxygen is actually the largest single element in slag, largest element in the slag, and about 40% by weight. So these we must have to aid in memory. So the basic building block is a tetrahedron with a silicon atom in the center and oxygen atom at the corner. That structure control how slag behave. Keep that image in mind as we move forward. So coming to our next slide, which is going to talk on a why should a furnace operator care about slag? Because slag control almost everything that matters. It sets the basicity, that's the balance between acid and bases. It determines how much slag volume we have, the temperature at which it becomes liquid, how easily it flows, that's the viscosity, and how well it removes the sulfur and silicon from the hot metal. Slag also affect alkali buildup. So when you take care of slag chemistry and properties, the furnace runs smoother, hotter and cleaner. That's the core idea. Now coming to the basic problem that why flux is getting added. So let's look at a real example. If you run a furnace with a only coke ash and iron ore gang, no added flux, we get about 240 pound of slag per ton of hot metal. So that slag is almost all silica and alumina with no lime or magnesia. So its melting point is extremely high, over 1500 degrees centigrade, and it's a thick like tar. It would not remove sulfur. So we add flux, lime, and dolo. That adds calcium and magnesium oxide. The flux pushes the slag composition to a lower melting zone on the phase diagram. With flux, we target around 500 pound of slag per ton of hot metal and how it flows well and removes impurities. That's why we add flux. So a very important questions has been taken care. So slag is not the same everywhere. So look at this table from the course material from which this reference has been taken. As you can see in the places around 37 to 41 silica is there, 7 to 10 alumina and high magnesia about 10 to 12%. Japan and Europe have more alumina 13 to 15% and less magnesia. India's slag volume is much higher, around nearby 400 to 500, and these is because their ore has more gangue. So alkali loading also varies a lot. So why does it this matters? Because your slag design must match your raw material and your furnace goals. So there is no single perfect recipe. So now question arises that what is the main norm we turn is basicity. How this basicity is to be kept control. So the simplest formula is the ratio of lime to silica. A typical range is 1.05 to 1.2. If basicity is too low, The slag is acidic, doesn't remove sulfur well, and can be too fluid at high temperature. So if basicity is too high, the slag becomes thick and pasty because you form high melting compounds like dicalcium silicate. On the ternary phase diagram, adding flux moves the composition along a line to a lower liquidus region. So basicity is a balance. We want it high enough for good sulfur removal, but not so high that slag would not drain from the hearth. So now coming to a very important aspects of the slag, that is about the viscosity. So viscosity is a measure of resistance to flow. For comparison, water is at temperature is 0.01 poise. Molten pure silica is 10,000 poise, like cold molasses. Our target blast furnace slag is between 2 and 5 poise. Fluid enough to separate from iron but stable enough to protect refractory. So look at this graph. At a given temperature, high basicity increases viscosity. Also, if your slag volume goes up, you need more heat to keep it fluid. That's why we monitor both viscosity and liquidus temperature closely. If the slag too thick, we adjust basicity or add flux. Now question arises that why desulfurization in blast furnaces and how it happens. So one of the most important job of slag is removing sulfur. The blast furnace is actually a very good desulfurizer, much better than BOF. So because BF slag is it has a very low iron oxide, only 0.5 to 1%. So BF slag has 15 to 25% iron oxide, and iron oxide block desulfurization. So the reaction is simple. Lime plus sulfur plus iron gives calcium sulfide and iron oxide. We use the sulfur partition equation shown here to predict how sulfur will split between slag and metal. The key is that higher basicity and lower FeO drive more sulfur into the slag. So to make low sulfur hot metal, keep your slag basic and reduce FeO. So then it works well. Now question arises here that here where the things get tricky, like sulfur removal is only feasible when your basicities are high, but alkali removal, specifically potassium, likes lower basicity. So look at this table. At a basicity of 1.1, we remove 2.6 pound of K2O per ton of hot metal. But if we lower basicity to 1, potassium removes jumps to 3.7 pound, a big improvement. Because potassium cycles, it reduces to gas in lower furnace and then condenses on the cooler body. If the slag is too basic, it traps less alkali. So we have a conflict. High basicity gives low sulfur, lower basicity gives low alkali buildup. So you cannot maximize both at the same time. So what to do? We don't just pick one basicity, we combine basicity and slag volume. So look at this table. At basicity 1.1 with a 550 pound of slag, we remove 10 pound of sulfur and 2.6 pound of K2O. Now drop basicity to 1 but increase slag volume to 580 pound. Sulfur removal stay the same, 10 pound, but alkali removal jumps to 3.7. That's a win. We have solved the conflict between hurting sulfur control. So the lesson is learned that when you have a trade-off, adjust two variables together. Lower basicity plus higher slag volume can give you the best of the worlds. Uh, of the world. So coming to the slag that doesn't go to the dump. So it's a valuable co-product. If we cool it slowly in air, we get a hard crystalline rock used for road ballast or aggregate. If we quench it rapidly with a high pressure water, that's granulation, it becomes a classy sand. That classy slag is highly reactive and is sold to cement plant to make Portland cement. There is also a pelletized version for lightweight concrete. So how you cool the slag determine its value. Fast cooling equals high value. Slow cooling equals lower value. That's important for the plant profitability. Coming to the box up phase. So let's wrap up. Slag is not a it's a not a just waste. It's a basically tool. You control it through the basicity, volume, and cooling rate. Remember the trade-off. Higher basicity helps sulfur but hurt alkali removal. You can solve that by adjusting slag volume. Keep viscosity in 2 to 5 parts range and always think about end use. Rapid cooling pays off. So next time you are on the furnace floor, remember, take care of slag and the furnace will take care of the rest.